Now, we shall be looking into mineral admixtures. So, module 3 lecture 3 deals with mineral admixtures, right. So, general outline of our discussion would be something like fly ash, silica fume, ground granulated blast furnace slag, rice ash cash, etc. These are all mineral admixtures, their production, characterization and some features of the mineral admixtures. So, that is what we will look into this lecture 3. Now, let us see what is fly ash. Coal is mined from mother earth and it contains clay as impurity. Now, you see thermal power plant burns this coal to produce energy which is used to generate steam and finally, to run the steam turbine to generate electricity. The fly ash obtained from thermal power plant, fineness is actually fly ash is obtained from thermal power plant, because this coal is burnt and it contains clay. So, when coal is grinded and burned to produce energy at about 1800 degree centigrade, the residue left after burning is fly ash. The residue left after burning is fly ash. In other words, it has something to do with the clay itself. Now, this is collected either in dry or in a slurry form. So, collected dry or is some sort of slurry form, and a small portion of this ash, as we call it, goes down, which we call as bottom ash. In fact, the ash that is generated, there is a clay which is heated up together with the coal, produces this ash which flies away, and some portion of the ash goes to the bottom of the furnace, that we call as bottom ash. So, we have fly ash and bottom ash. Fly ash generally goes above, collected through the chimney, collected through electrostatic precipitators, and then bottom ash remains at the bottom. So, let us see the process. The coal which is actually pulverized or made into fine powders, then there is a combustion occurs in furnaces. From the combustion, the flue gases will go through the chimney, and this is actually, this goes through what is called electrostatic precipitators, because fly ash being fine particle, they would have otherwise gone to the atmosphere, but generally considered as hazard from environmental point of view, health point of view. So, you do not want fly ash to go to the atmosphere and deposit in neighborhoods or elsewhere. It is kind of fine dust, very fine particle. So, not desirable that they get spreaded everywhere. Therefore, they are collected in the chimney itself using what is called electrostatic precipitators. They are nothing but electrically charged plates through which the flue gases passes, and since this fine particle forming colloidal solution in the air is colloidal solution in the air, since these are colloidal solution in the air, they are charged particles. So, these charged particles essentially, when they come across those electrostatic precipitators which have electrically charged plate, actually are precipitated and they are then collected, right. So, they are collected in electrostatic precipitators and followed by electrostatic precipitators, followed by fly ash production. This fly ash can be handled dry or wet process can be handled wet. So, why in wet process what you do? You actually mix up this ash with water and usually with the bottom ash, form into a slurry, and this slurry is transported and stored in a pond. In case of dry process, they are handled dry and taken directly to the silo. Wet process, put it into the pond. Wet process, put it in the pond. So, this is how fly ash is produced. It comes from the mother earth along with the coal. The coal gets burned into carbon dioxide, etc., but the silica or the clay particles, they form the ash. All right. So, that is what it is, that is fly ash. Now, this shows the fly ash production again. You see, this is the coal bunker, this is not cool, this is coal bunker actually, this is coal bunker, from where it comes to the pulverizer, this is coal pipe pulverizer, COAL, not COOL, coal pulverizer, and then from this, this pulverized coal is put it into the burning process or furnace, where from the flue gases will generate, compressed air is also passed in through this, this is put into the burner, and this burner would pass through the electrostatic, burned gases will pass through the electrostatic precipitators, and finally, the ash is collected from electrostatic precipitator. This ash is collected, if they are handled dry, they will go to the fly ash hopper, and if they are handled wet, they will go to the lagoon or the pond mixed up with possibly bottom ash. So, this is what is fly ash production. Schematically, if we look at it again to understand the fly ash as material, you see pulverized, this is first of all this is the this is basically the trucks or rail or roads, basically production from the power station. This is the precipitators, and from the precipitators some of them might go to disposal, some might be stored in raw pulverized fuel ash bunker. PFA stands for pulverized fuel ash bunker, and then they can be transported somewhere, right. So, this is from the chimney, the flue gas through the precipitator, this is fly ashes are collected and transported, and then you can put it into a classifier. So, therefore, if you put into a classifier, sizes, different size fraction can be separated, some may straight to be taken to the storage silos and may be transported through road tanker to various kind of processes, and here the oversized ones can be collected. So, you can process the fly ash somewhat, whatever fly ash you get from the chimney, electrostatic precipitators, they can be directly stored somewhere in silos, or they can be passed to a classifier where the large oversized or large sized ones are separated out, fine ones are taken handled separately, stored in a possibly silo, and then of course, transported by road or rail or whatever is required. So, this is how fly ash is produced and handled. If we look at the next one, another of mineral admixture material, it is silica fume. So, fly ash is one of the mineral admixtures, silica fume is another mineral admixtures. Now, silica fume is produced in silicon industry. Basically, you see silicon and ferrosilicon alloys in their production uses high purity quartz, and this is reduced with coal or coke and wood chips, basically with carbon, this is reduced to produce Si. So, these are reduced actually in electric arc furnace at around 2000 degree centigrade to produce silicon metal or ferrosilicon alloys. The semiconductor industry uses this material silicon and ferrosilicon. So, whichever industry uses silicon and ferrosilicon in their production, essentially quartz is reduced, that is SiO2 would be reduced to Si, and in presence of using carbon or coke or coal or whatever it is in electric arc furnace. Now, in this process some gases escapes, and this gases escaping from the furnace when condensed contains spherical particles of amorphous SiO2 in very high concentration, and this concentration of course depends upon the alloy type, right. For example, if you have 50% ferrosilicon, then you will have SiO2 content in the condensed silica 60 to 84%. For 75% ferrosilicon, this will be 84 to 91%, and for silicon metal 98% pure, you will have 87 to 98% of silica content in the condensed silica fume. So, this condensed silica fume is rich in silica, it is rich in silica, and that is how it is produced. That is how it is produced. All right. So, that is how it is produced. The schematic diagram would look like this, where A is the open furnace, B is the stack, C is the pre-collector, and D of course is a fan, E is the baghouse and filter. So, open furnace, from where this stack the gases goes, some of it is collected, condensed silica fume comes this way, the fume goes out and the condensed silica fume comes this way, it is collected, pre-collector is here, after that through the fan this is actually collected, baghouse and filters, that is how it is collected. So, silica fume is other mineral admixtures, fly ash is one of them, silica fume is other of them. Then we have got granulated blast furnace slag. Now, the two materials are the two extremes. Fly ash almost you get, it's actually, if you do not collect it, it is almost an environmental hazard, and therefore, this is available practically free of cost with transportation cost, because the thermal power plant or the power industry finds it difficult to dispose it of. It is generally an environmental concern. So, therefore, the power industry would like that as much of it is utilized elsewhere, and they do not have to pond, because you can't go on ponding or making what is called mounts out of them. In either case you need land, and you cannot go on acquiring the land again and again. So, for them disposal is a problem, therefore, it is available practically free of cost, whereas condensed silica fume it is not produced in all the countries, and therefore, it is produced only in some limited countries, needs not much processing, only little bit of processing in terms of condensation etcetera, but its cost is generally high in many countries. In India, of course, it is about 7 to 8 times costlier, mostly it is often it is costlier 7 to 8 times than that of cement. Fly ash on the other hand is practically available free of cost with transportation cost. These materials, they have a commonalities, all contains silica which can react, right. All they are common aspect of this material is all come from lime silica alumina system, they have silica and alumina. Second aspect common to these materials are they are grinded to fine and then heated to high temperature, 1200 to 2000 degree centigrade, and they are rapidly cooled, both silica fume as well as fly ash. Now, due to this rapid cooling, some chemical energy remains locked up as chemical potential, some chemical energy remains locked up, therefore, the chemical potential is higher than original parent material. Both these cases, in case of fly ash the coal has been heated, and in case of quartz, in case of silica fume quartz also has been heated, both are heated, contain silica and some alumina, of course alumina in case of fly ash, In case of silica fume, these are other materials are very less. It is usually the silica, SiO2 content is very, very high. So, both have been heated and then cooled rapidly, so that it could not reach to its naturally stable state. They are generally not crystalline, they are largely amorphous, and they can react in a conducive condition, right. Sometimes the clay impurity may contain a little bit of lime also in case of fly ash. So, that is why lime silica alumina system, they all belong to lime silica alumina system. Therefore, these are, as I said, they are relatively unstable because they are heated and then cooled rapidly. So, oxides that are present would be SiO2, Al2O3, some cases a little bit of calcium oxide, and some other cases it will be more, right. For example, in this case of course, it is high, but I have not come to the production of this as yet. So, this case is calcium oxide is high, and some fly ash has got high lime content. So, the oxides are similar or almost similar as the cement clinker, ordinary Portland cement clinker, but the proportions are different. This class of materials we call as pozzolana, that is why the title pozzolana we are seeing, and I will just explain what pozzolana is little bit later. Oxide content of course varies from material to material, that means SiO2 content in case of silica fume is very high, it is not so high in case of fly ash and even still less in granulated ground blast furnace slag. Rice husk gas of course, it is again high, we shall see that later on. Now, pozzolanic material has the characteristics that they contain reactive silica, as I said, because the silica which has been heated up and cooled rapidly is in amorphous relatively unstable form and can react with lime in presence of water to yield same product as cement hydration. We have seen when cement reacts with water, C3S and C2S reacts with water plus water, they gives rise to CHS. Now, lime is in this case of ordinary Portland cement clinker, lime and silica are mixed together, they are heated calcined to obtain the OPC clinker, but here the reactive silica and reactive lime you take, mix them together in presence of water, they will be reacting and they produce the same sort of product CHS. Okay. So, this reaction of lime with silica in presence of water is called pozzolanic reaction. So, the material which exhibit pozzolanic reaction we call them as pozzolana. Most of the mineral, not many, most of the mineral admixtures which you use in concrete are basically pozzolanic in nature. If you see the energy, cement kilojoules per kg, in case of cement it is 372. Lime if you want to produce, it will consume 173 kilojoules per kg, fly ash none. Hydrated lime 1.42 and burnt clay pozzolana, because you can burn clay, for example, metakaolin. When you take kaolin clay and calcine or heat it up to about 780 degree 800 degree centigrade, cool it rapidly, you get burnt clay pozzolana, or surkhi is also a burnt clay pozzolana obtained from brick kiln. When you making brick, we have clay which we mold into bricks, and when you heat up the fine powders as a dust which comes down at the bottom of the kiln, it is nothing but clay heated up to 1200-1300 degree centigrade and cooled rapidly. Surkhi is also a pozzolana, surkhi as we call it. So, surkhi could be one of them, these ones, and this one has also some energy required to produce. Rice husk ash about 12 kg per kg, surkhi is already shown here 12. So, they need much less, actually. So, this produces, so least energy is consumed in the use of production is fly ash, cement of course uses maximum, right. Granulated blast furnace slag has got somewhat higher value, some silica fume of course will have some slightly more than this. So, energy used is this. Right. Now, let me just explain before I go to this, let me just explain before characterization, let me just explain how do you get ground, granulated, blast furnace slag. You see, generally iron ore contains clay as impurity. To remove the clay, lime is added. Lime is added. This lime forms the slag. This lime forms the slag. So, lime is added. So, now lime forms slag. Lime forms slag together with slag. Lime forms slag, lime, clay and lime form slag, which normally floats over molten iron, floats over molten iron and collected, granulated and grinded, granulated and grinded to obtain GGBFS, ground granulated blast furnace slag. Rice husk ash is obtained from burning rice husk and slightly processing the same, So, all these materials they are obtained by burning some sort of silica alumina system at high temperature and cooling them rapidly. Characterization of these materials. We have physical characteristics. First thing, we look at grain size distribution, particle size distribution, fineness and also specific gravity. Now, grain size distribution is important because if you have more of the fine materials, if the particle sizes are finer, they can react at faster rate. Therefore, fineness distribution is one thing and overall fineness is also an important aspect. So, fineness, finer the material is, it will react more. Specific gravity is important because that will tell us how much volume do they occupy. Then we have chemical composition. We look at oxide compositions. So, oxide compositions like SiO2 content, Fe2O3. So, silica, iron oxide, ferric oxide, aluminum oxide, lime and alkali, magnesium oxide, SO3 etc. Loss on ignition is an important issue. This is determined by heating it up to 1000 degree centigrade, right, and keep it for half an hour. Heat it up to 1000 degree plus 50 degree centigrade, around that temperature. Keep it for half an hour. What will happen? All the unburned carbon, if present, will actually get converted into carbon dioxide and go away, but there will be some amount of moisture loss also. Any unoxidized material may also get oxidized. So, there will be net change of mass. Obviously, it will be usually the loss, because unburned carbon, depending upon of course the unburned carbon. So, loss on ignition actually is a measure of how much carbonaceous material, unburnt carbon is available, and this is an important parameter, because more of it makes it detrimental for use in cement based material or concrete system. So, chemical composition we look at it, these two important thing. Mineralogical characterization, largely this material should be amorphous, but there are some amount of minerals present. Of course, the the percentage of amorphous material is most important, more of it better it is, but still we look at the mineralogical composition, if there is any, whatever the minerals present there, right, we might look into by X-ray diffraction. Then of course, mechanical characteristics, that is most important. So, you look into mechanical characteristics, that is something like how mechanical characteristics are something like how much strength potential they have with cement, let us say, or with lime. So, these are some mechanical characterization, we will look into some of them. So, let us see physical characteristics. This is of course, in Indian scenario, the code that is available is IS 1727 1967, and following properties we can test. Fineness is measured by what is called Blain's permeability method. I think we discussed this when we were talking of cement. Fineness of cement is also measured by Blain's permeability method. And if you recall, we have a standard packing of the particulate system with a given porosity, and we achieve this with a plunger, and in a given container we pack it fixed mass of the material and pack it in a given manner, so that we get nearly same porosity, and then we measure what is called air permeability. In other words, for a constant head drop, the time required, flow, for the flow, how much is the time required for a constant head drop, that we find out, and from this time we can find out specific surface. Specific surface is related to the air permeability. So, you can find out the specific surface, and there is formula available. So, Blain's fineness gives us basically specific surface in terms of like cement, meter square per kg or centimeter square per gram, etcetera, etcetera. So, fineness is measured by this. We measure soundness like we do for cement. Is there any volume changes said with certain reaction? Lime reactivity is an important test, whereby we measure in fact the pozzolanicity. So, what we do is we make cubes with lime, pozzolana and sand. These cubes are prepared in a standard manner, 5 centimeter by 5 centimeter by 5 centimeter cube. They are prepared in a standard manner. Basically, the amount of water is fixed from the flow requirement. So, you have a fixed flow, for that how much is the water to be added, that is found out. The proportions used are 1:2 m. So, 1 stands for the lime of the particular grade specified in the code, analytical reagent grade. 2 m is m stands for the ratio of specific gravity of lime to the pozzolana, and then 9 standard sand. So, everything else is standardized except for the pozzolana, and then you produce the cube in a standard manner by mixing in a standard manner in a mortar mixer, and also making the cube in a standard manner, curing them in a standard manner, first 48 hours just under cover of glass and moist moist cloth or something like that, and then in a given relative humidity, standardized relative humidity for 8 days, and then test it for compressive strength in a machine, compression testing machine at fixed rate of loading. If you get the sufficient strength, then it is acceptable. A specified strength of the cube is given, and that is what we call as lime reactivity value. It is expressed in MPa, and if you get appropriate or minimum value of specified strength, you can use it in either in cement or in concrete, etcetera, etcetera. So, this is called lime reactivity test. Then we have got compressive strength of fly ash cement mortar, similar test, but this time we have cement, not lime and fly ash, but instead cement fly ash in standard proportion with cement mortar. Then drying shrinkage of fly ash cement mortar, not very important or common. Specific gravity can be measured by Le Chatelier's bottle, like we normally do for cement. So, same instruments are used practically, and also you can find out particle size distribution by hydrometer analysis, right. So, using Stokes law, which is done for soil, or also you can use particle size distribution by any one of the modern methods like X-ray diffraction, time of transition, laser time of transition, etc., etc. But in any case, one must understand that the particle size determined by one method is not comparable to that determined by another method. So, they are essentially comparative tool to find out fineness and particle size distribution. So, if you look at the physical characteristics of some of those pozzolana, then we will see that fly ashes mean size is 10 to 15 micron. Now, there are two types of fly ash, F and C. I think I will come to that later on. See, one thing at the moment we can remember is that type C fly ash can have more lime, up to 40%, whereas type F fly ash has got less lime in it, not more than 10%. And this classification is based on American Society of Testing Material, ASTM classification of C and F. Rice husk ash, if you look at it, it has got mean size 10 to 20 micron, mean size 10 to 20 micron, and silica fume 0.1 to 0.3, very fine, very fine, very fine. Metakaolin, which I said was a calcined clay, kaolin clay is heated up, calcined to 700 or 800 degree centigrade, and then rapidly cooled, they can have a size of 1 to 2 and micron. So, these are all in micron. So, this is in micrometer mean size. You can see the finest one is the silica fume, and the coarsest one would be possibly rice husk ash or fly ash. Blain's specific surface, if you look at it, if it is in meter square per gram, right, meter square per gram. So, if I write it in centimeter square per gram, that would be simply multiplied by meter square to send 100 into 10 100 meter square per kg would be how much? Kg would be 1000 times multiplied, right. Values, yeah, the value seems to be okay. It is of the order of around 1500 centimeter square per gram. So, 1.5. So, this centimeter square means 10 to the power 4. I think this is not correct. This should be multiplied by a factor of, this should be this divided by 10. There is some problem. I think the figure is problem. It should be 1500 centimeter square to about 3000 centimeter square per gram, whereas this is much higher. So, similar scale, it should increase the scale. This is not correct. This is not correct. Actually, the unit would be meter square, but relative values I think are same. So, this should be meter square per gram would have been then there is a multiplication of 10 factor. So, this will be relative scales are same, You can see that silica fume has got actually 15,000 to 25,000 centimeter square per gram. So, this is much higher, metakaolin is also higher, and rice husk ash is still higher. GGBFS is not so high, it is comparable to type C, type F fly ash. So, specific surface is much higher in case of silica fume, even metakaolin and rice husk ash, whereas fly ash has got low specific surface because particle sizes here are large, mean compared to this mean particle size is large, but there is a reason why this has got very large surface area, because this has got a cellular structure, cell like structure, structure will be cell like, something like this, cellular structure. I think I have some diagram, whereas these are spherical particles. GGBFS is grinded, so therefore, they are angular in nature, ground granulated blast furnace slag, so therefore, they are angular in nature. this is again spherical and these are platy. So, shape wise if you see this cellular, that is why this is shows much higher. Now, this is that is why that shows that is very high, that show very high. Specific gravity of the similar range except for GGBFS, which has got more lime than any other material, and all others have around 2, close to 2 or 2.2, 2.25, 2.4 etcetera, 2.4 etcetera, right. Okay. All right. So, this should be, if it is milligram, then how much it is. Anyway, this relative scale is fine. So, meter square meter square meter square per kg is around 150. So, meter square gram would be this should be multiplied, meter square per gram would be much less. So, divided by 1000, so 0.15, and if I multiply this by 10, so this should be millicentigram, maybe centigram Cg. So, meter square per centigram would be something like this. So, anyway, relative scales are fine. What we understand is this has got pretty high value of Blain's fineness, this has got somewhat much less, and this has got higher because of its cellular structure. So, silica fume is the finest of all this material. Now, if you look at scanning electron micrograph of this one of fly ash, you will actually see spherical particles, the white ones are spherical particles, these are spherical particles of the fly ash. So, generally they show spherical particles, sphericity, type C or type F fly ash, both fly ashes are spherical in nature, as you can see here, like it is something like this rounded shape, these are all rounded shape. So, this is rounded shape actually, as you can see here, right, rounded shape. So, silica fly ash particles are rounded in shape. Scanning electron micrograph, if you make them into solid by bonding with epoxy or something and look into their shape, ponded ash of course is the one which was collected wet, and this also has got spherical shape, but then there will be mix up of larger size particle. So, all look actually they have spherical shape, and there is something called plerosphere of type F fly ash. There are larger sphere in ponded ash, which will, if you break it, and you will find finer spheres are within them. There are some hollow spheres which we call a cyanosphere. So, fly ash particles is something like this. If you look at it, they are all rounded. So, they look rounded. So, actually they ensure that the shape that we have talked about, they are valid, and so is the silica fume. You can see that they are all black ones are the silica fume, they are rounded shape, microsilica as it is called, these are rounded shape. So, these are also rounded shape. So, scaling electron micrograph shows that they are rounded shape, fly ash as well as this. Now, rice husk ash, if you see, they turn out to be cellular in nature, there are cells. So, this is not rounded shape anymore, but you can see the cell sort of structure, cellular structure, that becomes visible, and that will depend upon at what temperature they have been actually burnt, 700 to 800 degree centigrade, this is 500 to 600 degree centigrade. So, depending upon the temperature, you find that their nature differs slightly, and at higher temperatures, see this shows the cellular structure of this material. They are cell like, you can see these are holes in between the solid phases. So, they are cellular in structure, and that is why their surface area was very, very large, or the particle sizes are not very large. If we look at the particle size distribution, the mass smaller than this size 100 micron, and this is 0.01 micron. C fly ash is here. There are, as I said, C fly ash has got lime, and class fly ash will not have, class F fly ash will not have lime. So, they have size very close to the cement, ordinary Portland cement, varying from 100 to 1 micron, right, 100% passes to 100 micron, and so is the case of cement. Calcined clay is somewhere there, relatively fine, and silica fume is the finest, because almost everything is smaller than, let us say, 0.3 micron or so. So, size wise we understand that this materials finest is silica fume, and the coarsest would be fly ash, metakaolin will be somewhere in between. All right. Rice husk ash of course is cellular in structure. The mineralogical composition, one looks at quartz, mullite, magnetite, hematite and glassy phases, because this is most important. So, these are the kind of minerals which are present, and one can obtain them from X-ray diffraction study. For example, this is for this is for fly ashes. You can see that quartz is present, mullite is present, hematite and magnetite is present. So, Q stands for quartz. In X-ray diffraction, what you do? It can find out the crystal, it can find out the crystal, because from angle at which the X-ray is incident 2 theta, where diffraction occurs from the the crystal planes, that is actually recorded, and this is mullite peak, this is quartz peak. So, you get quartz, mullite, these are the material which are present in fly ashes. So, there is a comparison of all of them. Low calcium fly ash, you see quartzite, mullite, etc. High calcium fly ash, again quartzite peak, etc. But granulated blast furnace slag, you do not get that many peak except here, but it is something like this. So, it is largely amorphous, and you can see this band which actually explain where you have got amorphous material. So, amorphous material is large quantity of amorphous material is somewhere here. So, these are typically the mineralogical compositions or mineralogical X-ray diffraction results of fly ash and GGBFS. More amorphous material in GGBFS compared to fly ash, which has got some crystalline material. Right. This is shown in slightly more details, low calcium fly ash and high calcium fly ash and GGBFS. So, classification, now I can talk about the classification of fly ash. There are two types. There are many ways of classifying fly ash, but ASTM classification is based on the lime content. Okay. There are other ways of classifying, but most commonly adopted classification is based on lime content, and that is ASTM classification. So, you have two classes, one is class F and class C, and that is what it is. So, class F or type F or type C. Now, type C F comes from anthracite or subbituminous coal, and they have low calcium oxide, that is the definition. Type C comes from lignite or bituminous coal, and they have got high calcium oxide. There are several other classification based on carbon content, etc., but this is the main classification. In fact, in India, northern India, mostly you get this fly ash. Somewhere in the south western region, you get type C fly ash. Wherever you get lignite coal, it results in burning of the lignite coal, results in class C fly ash. Let us look at chemical composition of all these pozzolanas. Type C fly ash, you will have silica 25 to 50%, but you will have calcium oxide 10 to 40%, that is what by definition. Type F fly ash, of course, you will have 35 to 60, but this will be less. Granulated, ground granulated blast furnace slags, you have got silica 20 to 40. So, this has reduced actually, but this has increased, lime has increased, because as I said, the blast furnace slag is obtained by adding lime to the iron ore for removal of clay. So, when you want to remove the clay, you add lime. Now, these two together forms a slag. Clay is removed by the lime and forms a kind of slag, which is again at very high temperature, same like other pozzolana, but it has got large quantity of lime compared to fly ash. Even type C fly ash, you will find more lime in ground granulated blast furnace slags. So, it has got more lime because lime has been added. Now, these slags usually floats over the molten iron. So, iron is drained out from the bottom and slag is taken out from the top, it is in molten state, then it is granulated, etc. So, therefore, it will have higher lime because that was added, and to remove the clay, and you have 30 to 50% of the lime, but then silica is less. Aluminum oxide is 5 to 35, and you see silica fume is slightly, it has got all silica, SiO2, large amount of SiO2, everything else is much less. This is small, aluminum is small, alumina is small, iron oxide is small, calcium oxide is small, glass content is very high in this, about 95%, whereas this has got 80%, but this has got less, as we could see from X-ray diffraction diagram, that this has got large lime, area under that curve is much wide, the bottom portion of the curve, and peaks where there are much less peaks in this. This has got about 95% amorphous material, this has got about 10% to 40% and 10% and 40%, and if you check it up in type F fly ash, you have got alumina, here this alumina gets reduced because this is infused. Iron oxide is 2 to 25, calcium oxide is low, but here calcium oxide is high. These particles are spherical, this is sharp, that is because you have grinded it. So, ground something which is ground material cannot be spherical, because after grinding it will be angular in nature, and this is again spherical, this is again spherical. So, these are the chemical characteristics of this. Now, IS 38 Indian standard 3812 gives specification of fly ash, it gives you specification of fly ash, 3812 gives you specification of fly ash and tells you what should be the chemical composition, preferred chemical composition, desired chemical composition of this material. Pozzolanic activity index is one of the index, right, like lime reactivity is in a way pozzolanic activity, it shows, because we tested cubes and the strength is measured, and that lime reactivity tells us about the strength potential of the pozzolana if you mix with lime. So, that is in a way kind of some sort of pozzolanic activity index, I mean pozzolanic indicator of pozzolanic activity, but pozzolanic activity index is defined in a specific manner. It is the amount of cement that can be replaced by unit weight of fly ash without altering the compressive strength at any age. So, let us say replace 20% C by F in mortar samples with standard sand. So, it is the amount of cement that can be replaced by unit weight of fly ash without altering the compressive strength at any age. That is how we define it, right. So, let us say 20% cement can be replaced by fly ash without altering the strength, then this is what is the pozzolanic activity index will be this. It is found out as A by B divided by 100, where average strength of the test cubes and B is the average strength of control cubes. So, strength should be similar. What is the fly ash, how much percentage of fly ash you can add, that you can find out, but in any case it should not be less than 75%, A by B less than 75%. Lime reactivity test I have mentioned, as I have mentioned is 5 centimeter side mortar, 1:2 m:9, m is the specific gravity of pozzolana divided by specific gravity of lime, that is m, and 2 is the standard sand. Compressive strength at 10 days, 2 days before demolding and 8 days at 60 degree centigrade, and relative humidity 90%. Quantity of water is used to maintain a fixed flow of 110 plus minus 5% flow, and then find out the strength after 10 days. If it is less than 4, if it is minimum is, it should be 4 MPa and 5 MPa for used in I think 5 MPa should be used in cement or concrete, 4 MPa for non structural work, etc., etc. So, this minimum value is specified, the cube strength should come 4 MPa at after 10 days. So, you test with lime the pozzolana and standard test you perform, and it must give you a minimum strength specified by the code. Minimum is 4 to 5 MPa, 5 centimeter side mortar, that is we have seen, and Blain's fineness is the other important aspect. So, therefore, what we have seen so far? What we have seen so far? We have seen what are the pozzolanic materials, what are pozzolanic materials, pozzolanic material from definition, they are the one which reacts with lime in presence of water. Lime water plus P would produce CHS. In fact, there is a little bit of history which I did not mention. The name pozzolana is derived from volcanic ash. Actually, volcanic ash, if you look at it, they of course are not naturally available everywhere, but available somewhere. This volcanic ash, particularly in Italy, volcanic ash when you mix with lime and water could give rise to production of cementing material, that is CHS. So, that ash was called pozzolana, and from that one the name pozzolana has come into practice. Name pozzolana has been derived from those volcanic ashes. So, all the materials which react with lime in presence of water to produce CHS like product, they are called pozzolana. They are used from quite Roman Empire, say 2000 years back they have been used. In fact, lime has been used for over 7000 years. That is what I think I must have mentioned in the very first day when I talked about the history of concrete system. So, pozzolana 2000 years back. In India, of course, surkhi has been used in many monuments. So, this use of these materials in mortar or masonry has been there for a very long time. Now, these materials are used as mineral admixtures in concrete. So, that is what we have discussed. What is pozzolana we have defined, and then we try to classify them. We try to classify them or name them in terms like fly ash, granulated blast furnace slag, some main ones metakaolin, rice husk ash and silica fume. And we have seen the extreme end, silica fume is the finest of them, most reactive, contains maximum amorphous material and amorphous silica. But and on the other hand, and in Indian scenario, of course, it will be the costliest of all of them. On the other hand, fly ash is the cheapest one, but its size is larger, it has got minimum specific surface, and but it is available free of cost. So, therefore, these materials can be used in concrete as mineral admixtures. So, we looked into their, first of all we looked into what they are, how they are produced, and then their physical characteristics, chemical characteristics and mineralogical characteristics. Finally, some mechanical properties. All right. So, I think with this we can we can conclude our discussion on mineral admixtures. Next class we will continue with the mineral admixtures, their effect on fresh concrete and their effect on durability and other issues. So, first we will look into fresh concrete, then their effect on hardened concrete, and lastly we will look into their effect on durability. So, I think we will conclude with this. Thank you very much for hearing.